Welcome to this second year of the LISM Cubed conference. So we should have a very interesting next 2 days. So just to give you a bit about the stats. So we're in our second year and we're expecting around 170 delegates in total this year. And that compares quite favorably to last year when we held this event where we had about 120. Hopefully the slide pointer works. Yeah. So just a bit about general housekeeping before we get started. So there are 6 fire exits at the back of this lecture hall. We are not expecting any fire alarms or tests today. So if you do hear the fire alarm, it will be a real event. If I could ask everyone just to keep their phones on mute, just to be respectful to the presenters and not to put them off track, that would be most grateful. And as you're aware, all the facilities, toilets and things are to the rear of the lecture hall. So just to give you a bit about background to us, your hosts. So my name's David Ainsworth. I'm CTO of OXIS Energy, have been for the last 4 years. So OXIS, as you know, a company dedicated to the development of lithium-sulfur rechargeable batteries. And the company has grown significantly in recent years to around 65 employees today, so quite a sizable SME. We'll also be joined with Dr. Greg Offer, who's an academic at Imperial College and leads a research group into a number of different areas of electrochemical devices, including lithium-sulfur batteries. We also have Dr. George Crabtree, who's a distinguished fellow at the Argonne National Lab and is a director of the J. Caesar team over in the US. And of course, this conference would not happen without the key people, which are the organizers, which is Tom Cleaver, who's the senior project manager at OXIS Energy and has done the bulk of the organizing with the facility. And also Jack Nichols, sorry Jack, your picture's missing from this presentation, but who did a lot of bulk of the admin related to the conference, as being a key individual in making it happen as well. So just a little bit about the overall conference and the venue. So we're at the IET, which is the Institute of Engineering Technology, slap bang in the middle of central London. As you're probably aware, we're only a stone's throw from many of the famous tourist attractions. And in the evening tonight, we have a very nice drinks reception, which has been kindly sponsored by Macor, where we hopefully can get a view of the city from the roof terrace. And that should be a good opportunity to discuss the technology as well. So we kind of expanded the scope of the conference this year from last year to include several parallel sessions. So we have one keynote speaker in each of the 3 areas of the conference: mechanism, modeling, and materials, and a further keynote lecture from the applications side. We also have several parallel sessions going on. So after the keynote this morning, we will break into 2 separate parallel sessions, and so you can choose which one of those you want to attend. So the kind of whole general philosophy of the conference is to sort of explore new opportunities, ways of thinking, so to encourage discussion, and hopefully we can have some nice ideas, some nice new strategies going forward from that. So the bulk of the conference will be videoed, so you'll be able to see the presentations online after the conference. we have the ECS have very kindly agreed to create a special focus issue around this conference and around lithium-sulfur technology. So I would encourage all the participants to support that initiative and provide information that can be published in that special focus issue after the conference. So this is just reiterating what I've already said. I think there's going to be a lot more dissemination activity after this conference, and I think the ECS special focus issue is a good opportunity to get more impact from your work and raise the impact of that. So I'd just like to say special thanks to the sponsors of this event. So this event has happened due to the REV-B project, which is a Revolutionary Electric Vehicle Battery project, which has been co-funded by both Innovate and the EPSRC. And that has allowed OXIS and Imperial College to be able to fund this event partially. Also special thanks to the sponsors, so Macar for the drinks reception, also the ECS for giving its seal of approval and giving the event some extra impact, and also our exhibitors, Graphinia and Renishaw, who have stands out in the poster area. So I think a good place to start on the technology side is just to draw a few comparisons to existing lithium-ion battery technology, the current state of the art in rechargeable batteries. So as you'll all be aware, or most of you will be aware in this room, the biggest difference is really the operational principles of the two different chemistries. So lithium-ion is very much solid-state intercalation process, well understood, whereas the lithium-sulfur system, a much more complex electrochemical conversion solution state processes. So that leads to a lot of challenges in the development of the lithium-sulfur system, but also leads to many of the opportunities as well. It's the fact that we have this complex chemistry which is able to utilize 16 moles of lithium ions per S8 molecule that gives rise to its high theoretical energy density. So I'm sure everyone in this room will be aware of the main sort of considerations for development of lithium-sulfur batteries. So the insulating nature of sulfur and lithium sulfide present some challenges. Also, the solution state nature of the chemistry gives rise to the common phenomenon of the polysulfide shuttle. And as is the case with most metallic anode battery technologies, lithium metal presents its own set of challenges, and I'm hoping that we can cover some interesting points on some research on that area during this conference. So to give you a kind of flavor of other things we'll discuss in this presentation, we first have to sort of understand why people are interested in developing this technology and why it's gained so much interest in both the academic and industrial community in the last decade or so. Greg, who follows me, will discuss some aspects of the mechanism, and that's an area he's been very heavily involved in over the last 3 or 4 years. And then we'll discuss broadly the challenges surrounding the main materials in the cell, so the challenges surrounding the cathode, electrolyte, and anode, and why the practical energy available from most systems today falls well short of the theoretical values. So firstly, why lithium-sulfur batteries? So most of you will be aware it's one of the systems with the highest theoretical gravimetric energy densities. I think it's fair to say that the volumetric side of the lithium-sulfur cell is pretty poor compared to a lot of lithium-ion technologies, and that's visible on the chart on the screen. But gravimetrically, already today, we're seeing cells, people developing cells around 400 watt-hours per kilogram. And that's very suited to applications that require mass over volume. So things like aerospace and space applications are very suitable applications for this technologies. Some vehicles where perhaps volume isn't constrained, larger vehicles such as trucks, buses, trains, and the potential for portable batteries where, again, volume might not be an issue, as in consumer electronics where volume is very constrained, but there's other batteries out there, particularly ones for military use, that lightness is more important than volume. So just lastly for me, there's a few operational differences between lithium-sulfur and other conventional battery technologies. So lower operational voltage has to be considered. I mean, this has a big impact on how you configure your battery system and your system architecture, and has a big impact on the control electronics in the battery management system. So because it's a solution chemistry, the mechanism is far more complex, and this makes it much harder to determine things like state of charge and state of health using simplistic methods, as is the case in the lithium-ion world. And also things like the resistance change over the discharge cycle, and that can cause its own set of challenges when trying to control large-scale battery systems with lithium-sulfur, utilizing lithium-sulfur technology. So with that, I'd just like to pass over to Dr. Greg Offer, who will now discuss a little bit about the mechanistic side of the lithium-sulfur system.
Thank you, David. Hello, everybody. Thank you for coming. It's a pleasure to see so many people. As David mentioned, we have more people than last year. Last year was the first time we ran this conference. It was more a workshop, more an experiment, sort of a one-off, and then it exceeded our expectations so much that we decided to run it again. And thank you so much to all the speakers who submitted abstracts. We thought this year we would do it entirely differently. We would run it as if it was a proper full international conference. So last year, most of the speakers were invited. This year, most of the speakers are self-selected abstract submissions. And as a consequence, this is the proof that that was the right decision to make, in that we have speakers from all over the world, many speakers that we haven't met before. And so it is great to see so many of you here. And I look forward to meeting you over tea, coffee, lunch, drinks this evening, and getting to know many of you a lot better. To just reiterate a couple of points that David made, the ECS paper is a real coup, a real opportunity, I feel, for everyone here. So it's open to anyone who's a presenter. In fact, even if you're not a presenter and you have a really nice piece of recent work, then please do send me or David or George an email and we'll send you an invite. It's the mainstream ECS journal, so it's not Transactions. It's the big one. It's the very high impact, premier electrochemistry journal, edited by Professor Doran Orbach, and it is open access at no cost. So this is really a great way of making sure that your research reaches as wide a possible as audience. The deadline is August, but it runs on a rolling basis. So if you have a paper, if the presentation you're giving today or tomorrow or your poster is already ready to go, you can submit tomorrow. And once it gets through peer review, it will be available online and essentially published within 10 days of being accepted after peer review. So please do take advantage of that opportunity. The other thing that I'd like to mention is David briefly mentioned the REV-B project. That has funded the collaboration between Imperial and OXIS over the last 3.5 years and also enabled us to support this conference. But there were 2 other partners involved in that project who, although they haven't directly supported the conference, they are presenting and they were involved in that project. So I'd just like to acknowledge the University of Cranfield and Ricardo Engineering for their involvement in that project. You will see presentations that will mention that work throughout the conference. So the purpose of this bit that David started is mostly just to give an overview of the science, the technology of lithium-sulfur batteries for anyone in the audience that it isn't their specialty already. And that was in response to a number of delegates from last year who said, we found it really interesting, but we would have loved just a basic introduction telling us some of the main things we need to know and consider so that when we're sitting through all the other technical presentations where you will go into the richness of the technical detail, it gives those people a bit more of an understanding. So for those of you who already know a lot about lithium-sulfur batteries, these might be somewhat tedious. For that, I apologize. But for those that don't, hopefully this will help the rest of the conference. So David already mentioned, the main attraction. Why do we like lithium-sulfur batteries? Well, it's the gravimetric energy density. That's a unique selling point. It makes it different from many other rechargeable batteries. But once you've overcome that initial excitement over that, very, very interesting facet, there are some challenges that remain to be overcome, which currently are restricting this to the niches David mentioned. Now, hopefully we'll learn throughout this conference about all the efforts, the international efforts around the world to overcome those challenges that will enable lithium-sulfur to expand into the mainstream. And I'm very confident that that will happen in the fullness of time. But to go through some of the challenges that we face, one of the challenges is understanding what goes on inside. Essentially, once the reactions get going and things are happening inside the cell, as far as we can tell, it kind of becomes a soup of lots of reactions all over the place. When we started our REV-B project at the very beginning, we worked very closely with one of my colleagues, Mark Wild from OXIS Energy, who's here, and we locked ourselves, the whole team of about 8 of us, we locked ourselves in a room for about 3 days. And we went through all of the papers that had ever been published on the mechanism and how and what reactions occur. And we put lots of paper all over the walls and we scribbled all over it and we tried to create a map of the lithium-sulfur mechanism. It was as complicated as the reaction map for photosynthesis, which is extremely complicated. And we looked at that and we thought, how on earth are we going to model that? It's impossible, because even if we do create a model that includes all those reaction pathways, parameterizing each of those steps would be impossible, because some of them we're not even sure they happen. Sometimes they're very specific to that particular solvent or that particular operating condition. And how do you design an experiment to measure the rate constant of a transient that only exists for half a second? So we tried to summarize it into groups of reactions, and this is what we came up with. And this is just the tip of the iceberg in terms of the richness and the complexity of the reactions. We then started, after that, we sort of asked ourselves the question, is there a universal working mechanism? I can tell you the answer is no. There are some constants. There are some things that will always occur and always need to be understood, one of which is the precipitation. But other than that, you just make subtle changes to the electrolyte, you put different salts in, you change the separator, and all of a sudden you can be kicking yourself down a very, very different reaction pathway. So there's a lot of work done by the diagnostics people, the characterization researchers around the world in the literature, a wealth of papers on the different in situ and ex situ techniques, which show that depending upon how you design your experiment, depending upon how you design your cell, you can have very different reaction pathways. So as a consequence, again, building a model becomes increasingly difficult if you need to capture the richness of those reactions. One of the other challenges is because you start with elemental sulfur, or in some cases people do start with the reaction product, the lithium sulfide, these undergo a phase change. And so one of the particular challenges is that essentially the majority of your cathode dissolves, and you're only left with your carbon structure, maybe with a bit of residual sulfur, and then you've got this soup of reactions occurring around it, and then eventually those sulfur molecules in solution are broken down into small enough pieces that they start precipitating out again. And so going through this solid to liquid to solid and then back again phase changes can cause very significant volume changes in a cell, structural changes in the material, and again, capturing that in a model is extremely difficult, and depending upon your reaction pathway can go through different paths again. The electrolyte is critical to designing a good lithium-sulfur battery, and what we see, and this is a story that will recur for the next few minutes, is that a lot of the work that we see done at coin cell level, although it offers great insight and is very useful and is the fastest and quickest way of developing new materials, unless the electrolyte to sulfur ratios are explored into the region where the electrolyte sulfur ratios are similar to those you have in a real cell, then you don't necessarily know whether the result you get at a coin cell is still going to work at a cell level. So this is something that when we read a lot of papers, we always have to treat them with a pinch of salt unless there is evidence that that work, it has been considered how that work would be scaled into a real device. So sulfur to electrolyte ratio is, for those people in the audience who didn't know that before, that's one of the big questions to ask. Sorry to mean that anyone who's in the material sessions giving those presentations, a bit of forewarning, make sure you've got an answer to that question when people ask it. So looking at the limitations, some of the challenges that we need to overcome, David's already mentioned the conductivity, the insulating nature of the beginning and the end product. I've already mentioned the dissolution of the active material. There's all these issues. The viscosity giving us that volcano of resistance is both a challenge but also an opportunity. That volcano plot enables us to do state of charge estimation, which otherwise is difficult when you have a flat voltage curve. One of the challenges to overcome is actually, this is sort of, I should give Tom Cleaver credit for this. Some of the next few slides where we've been looking through past research papers and doing a very extensive literature review, and you'll see what I mean by very extensive in a second. One of the consequences of that lit review was we came to this conclusion, and this is mostly Tom's theory, and I should add, does not, is a personal theory, and is literally just a sort of a curveball. This might not be a sensible thing to suggest, but it's something that we can discuss over tea, coffee, over a drink later as to whether anyone thinks that this argument is flawed or whether this argument has merit. So this is just a hypothesis that the primary unique selling point, that the strength of lithium-sulfur is the gravimetric energy density. But if we know that it's already good enough for some applications, and there's already customers willing to pay for the cells, there's a market, there's demand for them, then are some of the other challenges potentially more important? Rather than eking out another 10% improvement in energy density, could we instead increase that market for which the energy density is already good enough by looking at something else? And so one of the things that very few people look at is power density. Sort of the next thing on the list is often improving cycle life, reducing degradation. But at the moment, with most lithium-sulfur cells being relatively low rate, so you'll be using them at 0.1 C, maybe 0.2 C, every time a charge and a discharge test takes a long time. So it's expensive. You've got to have this equipment tied up for many years. And as soon as you make an improvement, as soon as you put a new additive in or you think you've solved something that might improve the cycle life, well, you have to wait years to know whether it's true or not. And particularly from a customer point of view, you need a large statistical sample size to prove to them that that result has significance. And so it's extremely expensive. If you instead spend some time to focus on improving the power density, then there's just one immediate benefit, which it speeds up the iterations. And so if you make an improvement on cycle life and you've got a power cell that can do 1C, then you've reduced the time it takes to prove that that has worked by 90%. And that significantly reduces the cost. So it's just an argument, it's just a hypothesis that maybe it would be interesting for some of the community to focus on power density. Because when we did the literature review, we literally found about 0.01% of papers have considered power density. So it's not suggesting don't work on the other things, but I think that there is definitely a gap for people to work on improving power density. And that was one argument we could come up with as to why that's a good idea. So the other thing that's often overlooked is the scaling up. And that's not a bad thing. I mean, we need a whole host of development being done from the ground up in order to try out all the new different strategies and see which ones work. But when a development shows promise, it then needs to be considered into how you would scale that up, because sometimes a new development that can't be dropped into existing cell manufacturing lines easily is going to struggle to compete against something that may not be as good but is easier to implement at scale. So it's something that is often overlooked, and you can't always extrapolate a result from a coin cell to a pouch cell. You need to consider what changes when I jump those length scales. It's not to say that you can't, it just needs to be considered. And that was something that we found quite often. So this was based upon some work that I mentioned, as Tom said. So this is just a very simple search. This is a few days ago, I just looked for the number of papers, Lithium-sulfur battery and Science Direct. You can see there's an exponential increase. Well, actually, there was an exponential increase up to 2015. It's probably starting to follow the traditional S-curve. So it seems to be that with the current sort of amount of investment internationally into lithium-sulfur batteries, it's probably sort of like a steady state of about 1,200 papers a year is probably what the current level of international investment is going to produce in terms of number of papers. That's a substantial international effort. Most of these challenges that lithium-sulfur currently faces, I fully expect to be overcome within the next few years with that much research being done. So in my mind, it's a really positive news story. It's a great technology that is going to get better. We then did, well, I say we, Tom did a huge amount of research. So of those papers, so far over 1,000 of them have been reviewed. So by extensive literature review, I meant extensive, as in the goal of this sort of mini project is to have reviewed pretty much all the lithium-sulfur papers that have ever been written. That is not an insubstantial task. Tom's already over 1,000. And he's categorizing all of those papers into what they studied, what they worked on, and the year, the exact subject. Whether is the paper looking at graphene, nanocarbon, other conductive materials. A huge classification system, which enables us to pull out quite a lot of trends. And it's from this analysis that we were able to identify what we felt were some strategic gaps. Where we would like to propose that to the international community of scientists and engineers as, these are some suggestions of things that we think are being overlooked, and could you please consider whether they would be of interest to you to study further. So from that, if we look at the analysis, essentially the vast majority of the people in the international community are working on the cathode. The cathode is interesting. Some of the major challenges to be overcome, as we mentioned, are in the cathode. So we're not by any means suggesting less work on the cathode. But if we look at the next largest thing, which is electrolytes, and yeah, absolutely critical. But when we begin to drill down into the other areas, particularly on the next slide, we can see that we break it down into the subcategories. And for example, on the right-hand side in the purple, which is sort of like other, there's a lot of work on technology overview, a little bit of work on cell design and component, and very little on cycling rates. So this led us to one conclusion, which is that there's a very obvious gap. There's relatively little on understanding charging, and yet that's half the life of a rechargeable battery. And so there's actually, we think there's a need to study charging, and particularly the mechanism during charging, the problems associated with charging, and actually some of our work, to plug some of our work, and Monica from my group is giving a presentation later where we show that one of the key bottlenecks of charging is the redissolving of that precipitate. So, and actually had a good conversation with one of the visitors yesterday over some work they'd done on actually improving power density. And they'd been able to charge one of their cells at 100 C or more. And so that was particularly interesting because we see that as a key bottleneck in improving the charging rate. The manufacturing and the production methods, as I've already said, are often neglected at a scientific level. And that's probably understandable because obviously OXIS know a lot of this stuff, but they don't publish it for obvious reasons. So it's not necessarily that the academic community needs to do basic research at that scale because it's less publishable and it's more commercial. But it's just more of a consideration when the materials research is being done, more of a consideration of how to scale up from the coin cell to the cell level would certainly be helpful in terms of understanding which of those materials developments are going to be suitable for scaling up. And then we saw very little work on the anode, other than sort of a cluster of work on protecting the anode into layers or better separators. And yet, really, to improve cycle life, it's all about the anode. And so a bit more work on the anode was identified as a crucial gap, considering its importance in mitigating degradation. So this work will be published, will be written up and submitted to this ECS special issue. So that puts a lot of pressure on Tom to read the remaining 1,000 papers in the next few months, which is going to be fun. But yeah, we might help a little bit with that. And then write this up and report some of these in a scientific journal. So there's a lot that remains to be done. We came up with a very long list of things that would be interesting to study further, and clearly most of these are being studied further by people in the literature. The list was almost exhaustive, but these were the ones that we thought were the things that would be most useful. So now I'm just going to skim through these because this is more or less giving a very amateur summary of the richness of the conference coming up. So the next 4 areas are materials, mechanisms, modeling, and applications. Essentially the 4 sessions of the conference. I should add apologies to the applications people. We came up with a nice acronym for the conference, Lithium-sulfur M cubed, and we came up with a nice logo, and then we thought, oh, applications are really important, but we didn't want to ruin the name or the logo or the acronym. So fitting an A into the LISM3 was going to ruin it. So sorry for the applications guys that your session. It is just as important as the 3 M's. I'd like to reassure you, because without the applications, without the demand, without the customers wanting these cells, then all of the work that the rest of us are doing is purely academic. So we have 3 parallel sessions on materials. We're expecting, talks at the cutting edge of research into most of these areas, if not all of them. There's posters that we're going to see on volumetric changes. There's studies on the precipitation and the insulating nature, the sulfur utilization, high surface capacity, a lot of the materials being developed to overcome these challenges. And there's so many different approaches being taken. And I see that as hugely encouraging. We only need a few of those solutions to work, and there are so many possibilities that it's almost guaranteed that some of them will work. So I see that as a great news story. And the material sessions are going to show us some of the best work being done from around the world. The electrolyte is just as important as the cathode. It's sort of part of the cathode. We've got speakers talking about new electrolytes and how they can be designed in order to overcome some of the challenges that we face. If you look at how much of the cell, a practical commercial cell, is electrolyte, good review by Kang, electrolyte can be 50% of the mass of the cell. So the electrolyte is a really important part of the system. And getting it right means that you can make a good cell. Getting it wrong means that you miss the whole point of lithium-sulfur, i.e. its energy density. If we look at the mechanisms are, as I mentioned, extremely complicated. I won't go too much into this because our first keynote, Celine, is going to be covering some of this and obviously presenting some of her latest work. As I mentioned, it's an extremely complicated system, and there's a whole wealth of tools and systems that have, and characterization techniques that have been developed over the last few years that can be brought to bear to understand what's going on inside. In terms of modeling, what we discovered is essentially in terms of modeling a cell behavior, we learned through the RevB project that we could essentially ignore the richness of that chemistry if all we need to do is predict the output voltage and temperature of a cell. Now, absolutely, if we need the model to predict internal states, concentrations of specific species for particular state estimation purposes, then we can't ignore it. But if we want a model for control purposes where we just need to match it to measurements from a BMS in order to do various state estimation purposes, then all you actually need is very simple models. And Monica will present some more on that in her session later today. The applications, we have a keynote tomorrow and some presenters tomorrow looking at the different applications. David already mentioned some of them where the unique characteristics of lithium-sulfur make them attractive already. And we'll hear more from people who are actually using lithium-sulfur batteries in real-world applications, the challenges they face and the things that they think we should focus on, hopefully. Because it's always useful to listen to your users and understand which challenges they think are most important, because they're often different from those that we come up with as the scientists. So I won't ramble on. The agenda is, you've all got copies of it. We have 3 sessions on materials, 2 sessions on mechanisms, 1 session on modeling, and 1 session on application. Some of them are running in parallel. Apologies to any of you if there were particular speakers that you can't watch both. It's obviously impossible to please everybody, but we've tried to think that if I was interested in that, I might not be as interested in this other one. But we won't have got that right for everybody. We've kept lots of time for social interaction. We think that's just that's the second most important part of the conference after the science, is talking to each other. So please encourage you, each coffee session or lunch break, go and talk to someone new, go and talk to someone different. That's what I'll be trying to do. And this evening over dinner, it is a bit cold. It was lovely and warm last week in the UK. This week it's a bit nippy. So if you want to spend some time on the roof terrace this afternoon, bring a jacket or bring a coat, because the views will be spectacular, but it will be a bit cold. And also, it is a free bar, so please do drink responsibly. I'm chairing the session first thing tomorrow morning, and I'd love to see most of you there. So please don't drink too much. And then, other than that, we would like to run this again. We think this is a useful service to the community. So please do give us some feedback. Let us know if you would like us to run it again. We are open to running it in different parts of the world. We think it could be good to maybe next year do it in the States or maybe in Southeast Asia. So come and talk to us. Please give us feedback. Come to the registration desk or send us an email, and we will take that into account. But for now, this is sort of a provisional date that we think we'll probably do it around about this time, so put this in your diary. Otherwise, perhaps, if there's just one or two questions for me or David, we can field them. Otherwise, we'll start the first keynote a little bit early and give Celine a bit of extra time. Okay, great. I will let David introduce our first keynote.
Just before I introduce the first keynote speaker, I'd just like to make just a couple of more admin points. If any of the speakers haven't yet provided their presentations to the conference organizers, either for later today or tomorrow, if you could please do that, that would help the smooth running of the conference enormously. And also for all the upcoming speakers in this morning's session, could you make sure again you see one of the organizers or technicians who will get you mic'd up 10 or 15 minutes just before you start your presentation. And again, that will ease the flow of the presentation session as well. So with that, I'd like to introduce our first speaker of the morning on the mechanistic side of lithium-sulfur chemistry. So Celine Barchez had completed her PhD in 2011 in the University of Grenoble. And since then, she has been at CEA in France as a leader of the lithium-sulfur research team there, and has published some very interesting work, particularly on in situ techniques for understanding the mechanistic side of lithium-sulfur cells. And some of that work is very highly regarded and very well cited. And also a special thanks to her for some of her great training on her staff members, some of which we have employed at OXIS today. So we have two former CEA employees of Celine. And with that, I'd like to introduce her talk. I think she's going to give us a bit of insight into some of those in situ techniques for lithium-sulfur analysis. Thanks, Celine.